Fine. Right. So you can see my
This
slides.
meeting is being recorded.
Amna, can you see the slides? I cannot.
No.
You can't see them. Hang on. Share screen. Okay. Now can you see them?
No.
Not yet, unfortunately.
Okay, let's try again. Sorry, this is okay, so let's see if I can share a tab. Let's see if this is going to do it. Yeah, let's.
Yes, we can see them now. We cannot hear you now, though. I think you're muted. We should be able to hear you now.
Can you hear me now?
Yes, yes.
And can you see the slides?
Yes.
Okay, brilliant. Right, let's go. So thank you so much for this invitation. I'm always really delighted to talk to talk to whoever, but I'm particularly interested in communicating to women and people outside the normal group of people that I would talk to. So I'm going to talk about the assessment of the ocean cryosphere and sea level change in the 6th assessment report. So I'll talk a little bit about the IPCC process and my role, and there's a few little pictures from various stages of this. And then I'll talk about ocean changes that we've assessed, about the cryosphere changes, including glaciers, and sea level rise. And then hopefully there'll be plenty of time for questions. So first of all, what is the Intergovernmental Panel on Climate Change, or IPCC? Well, it's the United Nations body which assesses the science related to climate change, and it provides policymakers with scientific assessments on climate change, looking at the impacts and potential risks and options both for adaptation, so how we can adapt to changes which are already happening, and also mitigation, so how can we prevent more changes from happening. So there are 3 reports in IPCC which are called Working Group 1, 2 and 3, and I was involved in Working Group 1, which is the scientific assessment, but I talk with people in Working Group 2 and Working Group 3, so there's there is a dialogue which goes throughout the working groups. So this was the kind of, it's a long process, thinking that we had the report published in August of last year. Originally, it was scoped back in 2017. So the governments agree what the outline will be, then authors are nominated. So I started working on this at the start of 2018. So yeah, so the last 4 years of my life, really. We write drafts, so we have 3 drafts which go to review to experts and to governments, and then finally we write what we call the SPM, or the summary for policymakers, and that is like a very short summary, a very thin book of all this assessment, and that is approved at an approval session where all the governments can participate, and it's like a co-production process. We put it forwards and then they have questions and make suggestions, and eventually then that goes through, then that's approved. And then in what's not on this figure but obviously was unique to this year was that the COP, or the Conference of the Parties, was in November. And so the IPCC report of Working Group 1 was very new. So that was presented at the COP meeting in Glasgow. And you can see online videos of the structured expert judgment and the presentation to all the governments. And we can talk some more about that at the end as well, if people are interested. So the Working Group 1 report had 234 authors, which came from 65 different countries. There's in the process of choosing the authors, there's a big emphasis on diversity, both in terms of men and women, and in people new to the IPCC, and covering as many countries as possible. So you can see we're not equal, men and women, but you know, we're trying to kind of build that number and the number of countries that this spans. So in terms of the assessment, we can you see my pointer?
Yes.
Yeah, we assessed as a whole, we assessed over 14,000 publications. When we sent the chapters to reviews, they came back with review comments. The report as a whole had 78,000 comments. My chapter had 10,000 comments, and I've written, you know, quite a lot of papers, but I don't think in total I've ever answered 10,000 comments. So that's, you know, there was a team, but that's still rather daunting. And 46 countries commented on it. So this was the outline. So the report sort of split into 3 parts: a bit about large-scale climate change, a part about climate processes, which is where the ocean, cryosphere and sea level chapter comes in, and a part which is more focused on regional climate change. However, I would say that chapter 9, which I worked on, very much interfaces both with the large scale and in the regional. And so I hope that will sort of be reflected when I talk about it. So the way IPCC has been done pre-COVID is there's been lead author meetings in different places. So we had a meeting in China, we had a meeting in Canada, we had a meeting in France. We would have had a 4th meeting, and then COVID hit. So we actually finished the report in a completely virtual sense. And when it came to the approval session, where we would have been in one place, we actually did that online for 2 weeks as well. So it's completely changed things, and I have to say I think that's a good thing. It's you know, it can contribute to reducing the carbon budget by doing things virtually. So this was our chapter. So our chapter had you know, 3 coordinating lead authors, which I was one of, a team of lead authors, review editors, and we also had 5 chapter scientists working with us and 74 contributing authors. So it was quite a mammoth undertaking just for even just for our chapter. So what did I do? So as a coordinating lead author, I co-led the whole chapter team. We worked really hard leading the chapters to work on inclusion, so making sure that everybody's voice was heard, and that we really did span all the literature. I directed the scientific assessment, the technical production of the chapter, and the responses to the review comments with the other coordinating lead authors. I contributed personally to the scientific assessment, so I think my expertise has gained both some depth and breadth. We coordinated with the co-chairs, with other chapters, as I said, other working groups. And really now I'm kind of, you know, see my role as really being a spokesperson for the chapter, particularly as part of the results in the summary for policymakers, and beyond this to outreach as well. So I think it's really good to emphasise that IPCC is an assessment of the scientific literature. And for that, we have what we call a calibrated language. So we look at all the evidence, and we try and look at agreement and the type, the amount, the quality, the consistency of the evidence. And then, so when you read an IPCC report, you'll see it littered with terms like low or high confidence, limited agreement, or high or robust agreement. And so, or robust evidence rather, and so that's part of our language. and then also we talk about whether things are likely or very likely, and these have very specific percentages related to them. So we can talk some more about that if that's of interest. So now I'll talk about the results. So it's very much a whistle-stop tour of the whole chapter. So I hope to give you a real flavour of what we looked at. So first of all, think about the ocean. So you know, one of the key messages obviously is the planet is warming, but the oceans are taking up 91% of the heat of the planet. And the upper 700 meters of the ocean alone is taking up 56%. And you can see here in this figure that increasing over time. So this is time from the 70s onwards, and we choose the 1970s because before that we had very few observations of the subsurface ocean. And you can see this block here, that the upper 700 meters are continuously taking up more heat. But you can see really since the 1990s that now this heat is getting into the layer down to about 2,000 meters. And so particularly for heat, it's all going into the ocean. There's a small amount related to ice, land and atmosphere, but you know, you really see the vast majority in this blue colours. One thing that's really important in terms of impacts related to the warming of the ocean is marine heat waves. So these are sustained periods of high sea surface temperature, and they have severe impacts for marine ecosystems. Coral reefs, for example, can be bleached really badly from a marine heat wave. And as you can, oh, that was not what meant to happen. As you can see from this figure in the time series, the marine heat waves have become much more frequent over the recent periods. You see in the orange line. And when we look to the future and we look to different scenarios in the future, so in this case, what we would call 2.6, which is a low emission scenario, or 8.5, which is a very high emission scenario. Even in the low emission scenario, marine heat waves are projected to become more frequent. Even under this low emission scenario, on average 4 times more frequent by the end of the century. So as well as the temperature changing in the ocean, the salinity of the ocean is also changing, because as the atmosphere warms, the hydrological cycle intensifies. So this means that places where you'd get evaporation become more evaporative. Places where you'd get precipitation or rainfall will experience more precipitation. And you see this in the ocean salinity. So where the water is fresh, and you see that, for example, in the Southern Ocean, in this water here called Antarctic Intermediate Water, that's becoming much fresher. And in the subtropical gyres, so you see here, and they're very saline because they're very evaporative, they're becoming more saline. So this is a whole paradigm with the fresh getting fresher and salty getting salty in the ocean. So as well as the temperature and the salinity, we'll also look to the circulation. Now, I know Pakistan's quite a long way from the Atlantic, but one of the main drivers of the global circulation is the Atlantic meridional circulation. And this defines a conveyor belt which goes all around the globe. What we assessed was that we've got low confidence in what's happened in the past with the overturning circulation, because we had different sources which didn't agree very well. But because we understand the mechanisms, we know that it's very likely that the circulation will decline in the 21st century. And there's some limited evidence from an array in the ocean which suggests that there is some hints of it already declining. And we also talk about whether it will collapse completely, which would have big impacts on the kind of weather around the world. And we note that while we think there will be a decline, there's medium confidence that there will not be an abrupt decline, abrupt collapse before 2100. Are you still there? Everybody still there?
Yes.
Yes, we are.
Good. Okay, so so this was actually I just wanted to move on just to talk about two other aspects of the ocean, about the acidification and the oxygen, and these were actually talked about much more in chapter 5 of the report, but they're really relevant to chapter 9 as well. So as well as the oceans taking up heat, they also take up carbon dioxide from the atmosphere. And when the ocean takes up carbon dioxide, this leads to acidification of the oceans. And so if you look in this figure, this is showing the pH, or the acidification of the surface ocean. And if you look all around the globe at time series of this in different of the ocean's pH value in different places, you can see it's there's a very clear pattern of declining throughout the globe, and that's at the surface. If we look at a section that comes down through the Arctic, right down through the North Atlantic, through the Southern Ocean, and then up through the Pacific, and also a section through the Indian Ocean, you can see that this is where the pH is becoming more acidic, so going towards being more acidic, so lower pH values. And you can see it's not just in the surface, it's also penetrating into the deeper ocean. And this, this also has severe implications for the marine ecosystems. If we look to the future, so this is a simulation of the past, which agrees well with the observations on a global average. And if we look at scenarios into the future, in a low scenario at the surface, the pH may recover a little bit, but with higher emission scenarios, we're just going to move towards more acidic values in the ocean. Another kind of key feature for marine ecosystems is also the oxygen. And so as well as becoming more acidic, the ocean's also is losing oxygen. So when the ocean becomes warmer, and the ocean's also becoming more stratified, which means that it's much harder to mix water down from the surface into the deep ocean, it stops oxygen from entering the ocean. And we can see this in periods of warming in the past, in paleo measurements. So it's virtually certain now that the upper ocean has become more stratified. This was one thing that had changed quite a lot from the previous IPCC report. We're now seeing a much greater increase in the stratification. We know we're seeing the warming I talked about earlier. So it's not surprising with that we're seeing this this decline in oxygen. And so there's now high confidence that that it's occurred since the mid-20th century. Oxygen minimum zones are expanding, and this will continue throughout this century. So that's a kind of brief overview of the ocean. Now I want to turn and look at the cryosphere. Now there's lots of components to the cryosphere. There's the sea ice, there's snow, there's permafrost, there's glaciers, and there's also ice sheets. And these all respond on different timescales. So Arctic sea ice, snow and permafrost respond very rapidly to global temperature change. So for example, if you look at this middle figure here of the snow, and this shows the snow cover change in percentage as a function of temperature, you can see that the decline in snowfall is very strongly, snow cover is very strongly related to global temperature. The same is largely largely true of permafrost until you reach a kind of threshold of about 3 degrees, where there's very little permafrost left. And it's also true of the sea ice as well. So both in the March Arctic sea ice and in the September Arctic sea ice, they're both strongly related to global temperature. So we know that in the case of these, if global temperature were to recover, these parts of the cryosphere would have a chance of recovering quickly. On the other hand, glaciers will take decades to respond, and the ice sheet, so the Greenland ice sheet and the Antarctic ice sheet, will take millennia to recover. So I'll talk a little bit about all of these, and just to note that mass loss from ice sheets and glaciers is really is particularly important in terms of global sea level rise. But you know, I know particularly in your area that glaciers are really important for water supply as well. So there are other reasons to be concerned. So just to say about Arctic sea ice, so the Arctic sea ice melting, the Arctic we project to be ice free at least once by 2050, and more frequently with higher emission scenarios. If the Arctic sea ice cover disappears, this has implications not just for ecosystems but also for shipping, for example. So global trade. There's high confidence not just that they've declined since 1850, but they're at their lowest now. Since that period, we have medium confidence that they're at their lowest level since in the last 1,000 years. And looking to the future, as I said, we're seeing this pattern where the Arctic's becoming ice-free. So moving to glaciers. So over the past 20 years or so, well, nearly 30 years, glaciers contributed 17 millimeters to sea level rise. The mass in a global sense of glaciers in the last century is at its smallest since any decade in the 20th century. And there's medium confidence that this global nature of glacier loss is really unusual in the last 2,000 years. So if you look in this figure, now this is split up into regions. So the glaciers from each region are put together. And so, you know, regions which are particularly relevant to you, I guess, are these, the Asian ones, the high mountain Asia particularly. But if we look as a whole and you look at the brown and the blue lines, which are reconstructions and observations of the glaciers in these regions, you can see how there's this loss in all the regions, and that's not been seen in the last 2,000 years. We can project them out to 2100 with different models of the glaciers, and this suggests that we'd expect between 18 to 36% of the current mass to be lost by the end of the century. So that's for the global glaciers. Now, in particular, if we look at we assessed glaciers in different regions as well. And if you look particularly at the Karakoram anomaly, which was talked about in previous reports, in that region, you know, we still think in the recent past, the glaciers in that region are close to balance, or perhaps, you know, even in the last decade, slightly gaining mass, which is kind of unusual in the global sense. And there are, you know, we looked at the processes of why that might be the case, and that points to the fact that you know, are not unusual in more populated areas. There's debris on those glaciers, which changes their sensitivity to temperature. In the region as a whole, there's actually decreased air temperature in the summer, and that's due to a change in the circulation. And there's also some signs of increased snowfall, which has been suggested to be related to agriculture. However, the assessment did suggest that this anomaly is unlikely to persist in the 21st century, which doesn't mean that it won't, because unlikely only means that we've got a 66% certainty. But nevertheless, that is the direction we think it will go, and that's what the projections would suggest from the models. So I'll just say something about the ice sheets as well. So the Greenland ice sheet contributed a bit less actually than the glaciers to sea level, but its rate of mass loss is increasing, and I'll show you that in a bit more detail later. The ice sheets have a huge amount of water stored in them, so they have a big potential to add sea level rise. So Greenland, for example, has about 7 meters of sea level contained in it. So it's virtually certain that the Greenland ice sheet will lose some of its mass over the 21st century. What we're seeing is that if you look at these observations, that the marine margins are melting from the glaciers at the coast, and so they melt from the surface, and the centre of Greenland will become increasingly important. What we do when we look to the future is we have some model experiments, which are these blue and red lines, but we really wanted to know about other scenarios so we can look at details. So we developed what are called emulators. So you sort of like statistical models of the models, if you like, and this allows us to extend to all scenarios and to explore some of the uncertainty. And so this suggests that by 2100 we might have 20 centimeters added to sea level from the Greenland ice sheet. But there are, when you look at high resolution projections, which include the glaciers in more detail, this does point to the possibility of higher loss. And similarly, we also looked at the Antarctic ice sheet. Well, I'll come back to this. I'll show you again. But you can see in warm periods in the past, the ice sheets have been much smaller than the present day. And in cold periods, such as the last glacial maximum, they're much more extensive. So the Antarctic ice sheet has contributed even less than Greenland and glaciers in the recent period, but it is likely to lose mass over the 21st century. It is a particular concern because it has a very large amount of potential water stored in there. So, 60 to 70 meters of sea level if it were all to melt, which isn't going to happen in the 21st century. And even in these warm periods, it's mostly West Antarctica which was lost, which is closer to the amount of Greenland. Again, we used emulators to extend this, and in this case we looked at different emulators, and it tells us that it's really important how much water goes under ice shelves to melt them from below. And so with those sort of scenarios, you could have up to 40 centimeters of the global mean sea level added if we had a lot of melting from the ice shelves. There's also deep uncertainty around marine ice cliff instability, which I'll talk some more about later on. And if that happened, it would increase the mass loss a lot. So one thing that people want to know is that what will happen if we pass certain temperature thresholds. And so we looked at this for various things, but particularly for the ice sheets. And so, as I said, we've seen in the recent past, so in the mid-Pliocene warm period, which was more like about 3 degrees, and the last interglacial period, which was more like 1.5 to 2 degrees, you can see that the ice sheets were much less extensive than they currently are, both in Greenland and in Antarctica. And so we assessed that between 2 and 3 degrees, there's limited evidence that Greenland and West Antarctic ice sheets will be lost. So all of Greenland and some parts of just this western part of Antarctica. But this will, the warmer the temperature is, the more likely we are to experience the loss. As we go to 3 to 5 degrees, near complete loss is projected to occur irreversibly over multiple millennia. So there's long time scales are involved here. So moving on to sea level, which as I've said, it involves a lot the glaciers and the ice sheets. So sea level rise can occur from 3 different reasons, at least in the global mean. So as the ocean warms, it literally expands. That's known as thermal expansion, and that increases the volume of the ocean. So that's like having a glass of water, making the water hot and just seeing it take up more space in the glass. You can, as glaciers and ice sheets melt, that would literally pour water into the ocean. So that's like adding water into the glass. And also, if we change land water storage, this can affect the global mean sea level, but that's a much smaller effect than the previous two. As I said, the glaciers as a whole over mountains could add up to 30 centimeters of sea level. Greenland, if it all melted, which is a millennial process, has 7 meters stored in it. Antarctica, in this figure, sorry, correct what I said earlier, says 58 meters. But that's very, very unlikely. So what have we seen in sea level rise? So this is a time series of the global mean sea level over the last 2,000 or more years. You can see that in this recent period here, the recent century, global mean sea level rose faster than any prior century in the last 3,000 years. In the last century, it rose by 20 centimeters. But what's also noteworthy is that the average rate of sea level rise is accelerating. So it started off more slowly at the beginning of that century, and now it's much faster. If we look at the causes of that, so just added in this extra figure here. Just checking, are you all still with me?
Yes.
Yes, good. We can see that this is where the sea level contributions have come from. So unlike the warming, which mostly came from the ocean or stored in the ocean alone, the sea level comes from various contributions. So back in the the 80s, 90s, the main contribution to sea level rise was from the upper ocean warming, this top 700 meters, and from the glaciers, which is this grey colour here. If we look over the more recent decade, and not only has the contribution from ocean warming to sea level coming from deeper in the ocean as well, which is perhaps what we would expect. The contribution from glaciers has continued, but this contribution from the ice sheets is now accelerating, and that's increased by a factor of 4 in recent decades. We know that human influence is very likely the main driver of these increases. And I'll talk about the future projections, but if you consider just historical emissions up to 2016 alone, global mean sea level will be expected to rise by between 70 centimeters and 1.1 meters. And that's without extra emissions moving forwards. And that will be by 2300, sorry. So we made new projections of the future of future sea level rise. So what do you see in these projections? And so, as I said, these projections are different emission scenarios. So the green is very low, going through low, red is high, and the darkest reddy brown colour is very high emissions scenarios. Probably at the moment we're kind of on a path somewhere between about the yellow and the red, so between what we call SSP 2.4.5 and SSP 3 7.0. And I should have said, sorry, that SSP stands for shared socioeconomic pathways. So they make lots of assumptions in how these emissions pathways are developed. Now, if we look to the future of global mean sea level rise, you can see that to 2050, there's very little sensitivity to emissions. And what this is telling us is that what we've done in the past has already committed us to how much sea level rise we're going to see by then. So, around 15 to 30 centimeters in the global mean. after that period, the choices we make will become much more important. So by 2100, if we were on the low emission scenario, we would see between 30 and 60 centimetres. If we went on the high, not the very high, the high emissions pathway, we'd see between 55 and 90 centimetres. So, and then this continues out to 2150. So you can see that there's a lot of variation in this. And we also considered processes which we didn't understand so much, which we would call low confidence processes. And those could give higher sea level rise, as you see but we only applied this to the very high and the low emission scenarios because we didn't have enough information on the others. So if we look at why that would happen, so for example, if we look to 2100, first of all, you can see that this would be what we call a low likelihood high warming scenario. We'd have ice sheet instabilities around Antarctica, strong mass loss from Greenland, and this could add up to an additional metre of sea level rise by 2100. Obviously what people are interested in is regional sea level rise, but so regionally we know that we'll expect to see more frequent and severe coastal flooding in low-lying areas and more coastal erosion. Most coastal locations have a regional sea level rise which is within 20% of the global mean sea level change. And if people are interested, we have this really nice tool which you can go to, and you can look at tide gauges from a place close to your location, and it shows you the recent past and the possible futures. If we look beyond 2100, as I said, we already have some commitment to 2300, but under a high emission scenario, we could see up to 7 meters of sea level rise. But if we have this process, which is known as marine ice cliff instability, become important, and that's a real uncertainty, which we're not sure how important this will become. But if it became important, we could see up to 15 meters of global mean sea level rise by 2300. And that's definitely an area where scientists are going to be working on a lot to try and narrow down these projections on these longer timescales. So if we, sea level rise will continue. We've committed to it for centuries. It will continue for millennia and will remain elevated for thousands of years. We saw this in these recent past periods of the last interglacial and the mid-Pliocene. And, depending on where we stabilise global warming will depend how much we are committed to. So if we could limit to 1.5 degrees, we might see 2 to 3 meters. If we exceeded 5 degrees, we'd be committed to these big global mean sea level rise numbers of 19 to 20 meters over a few thousand years. And these agree with reconstructions from the past periods. As I said, we expect to see more frequent coastal flooding. Events which might have occurred once per century may occur annually or more frequently, at 60% of tide gauges in a low emission scenario, at 82% of tide gauges under a high emission scenario. So the choices are very much in our hands still, I think, in terms of the future. So just to summarise, the changes we're seeing in the ocean and the cryosphere are really unprecedented. We see in a number of places that changes are unusual in the context of the last 1,000 years, the last few million years, and so this is very striking. We can also say that many of these ocean and cryosphere changes, as shown by the red arrows, are where human influence has been the main driver of the changes that we've seen, or at least has contributed to. So you see that in the red and the yellow arrows. And not just that, but looking into the future, it's not just in the global mean, but they're going to be widespread in where we see them. And so we have these climate impact indicators, drivers, which cover the cryosphere and the coastal regions. And you see very strong agreement in all regions of how this is going to pan out. So in all regions, we'll see like melting of snow and glaciers and the ice sheets. We'll see more marine heat waves in all regions, for example. So it's very stark, this strong agreement. So, and if we look to the summary for policymakers, we see that you know, the messages from that hopefully I've talked about are in this summary for policymakers. It's really unequivocal that the ocean and cryosphere are changing. They're widespread, rapid, they're intensifying, unprecedented, as I said. Extreme events such as marine heat waves, but also coastal flooding are becoming more frequent. And while some of the cryosphere loss increases in direct relation to global temperature, so could be restored more quickly, many changes are due to the past and future emissions are irreversible for centuries to millennia. And some of these low likelihood, high impact outcomes, like the marine ice cliff instability, we can't rule these out. And so I'll just leave you with this. This is this cover of the summary for policymakers, and this is one of the figures in there which I worked on. And I think this really encapsulates one of these quotes, you know, the recent changes are widespread, rapid, intensifying, unprecedented, and there's no going back from some changes in the climate system. However, on a more positive note, some changes could be slowed and others could be stopped by limiting warming. And just thanks and happy to talk.
Thank you so
Stop
much.
sharing.
Yeah. Thank you so much. That was a wonderful presentation, and it's always spellbinding for me to see how thousands and thousands and thousands of people actually come together, and scientists too, like basically scientists, to write all these reports. And it's a magnificent thing if you think about it. And I have I have literally millions of questions, but I will keep them to myself for now, and let Dr. Parveen take over. And so I saw somebody raise their hands. I believe it was Ikra. So if you would like to ask her.
Amna, do you want me to continue, or are you giving the floor to?
Yes.
Okay, awesome. Thank you. Thank you, Dr. Helene. That was really, really enlightening. And also, I meant to read the long report, but I think after your presentation, you've saved me a lot of time. So I'll just stick with the shorter version, and I think it saves us a lot of time as well. So thank you for you know, giving us the opportunity to listen to you, and of course, a big thanks to Dr. Amna for organizing this. Because Amna had been a part of the COP26, and we were talking about, you know, the processes in general when she got back. This may or may not relate to you directly, but, you know, because you are just a part of the scientific community, but in a way, the content of the report is communicated with governments and how governments feel about the reports and, you know, the certain changes that they would ask you to make in the report. Particularly, for example, in the COP26, we saw that some countries strongly disagreed with the inclusion of high impact, low likelihood events. So I think as a scientist or an academic, it'd be difficult to draw the line, but also for IPCC, because the credibility is at stake as well. So where do you, in terms of the parties or let's say the governments who then eventually have to sign and agree to it, draw the line in terms of quality and quantity as well?
Yeah, well, I think what I would say is that obviously everything goes through an assessment. So, you know, the low likelihood, high impact outcomes, for example, they are definitely, you know, low confidence, because there's lots of processes there we don't understand. And you know, they're definitely presented in that way. I think I think a good analogy of the low likelihood, high impact is the pandemic. You know, it's I think it's good, and a lot of policymakers, I think, find this really helpful from talking to them, as that they want to not know just the you know, the most likely options, but the worst case scenarios as well. because then I think when you're making, you know, and then they can make their own risk assessments, like are they happy to just kind of you know, assume that they'll be limited to 1 meter of sea level by 2100 or 2150, or do they need to plan for several more meters? And so I think presenting the evidence allows them to make that choice. So I know it's difficult, and you know, there was a lot of debate, as you can see on the record, in the structured expert judgment. There was in the approval session for IPCC about this inclusion, and in the end, you know, I think the majority of governments wanted it in. So therefore, in terms of the co-production process, then, you know, that in that case, you know, all the governments agreed in the end that they would accept that's its inclusion. Does that kind of help? As a scientist, it was a very strange process for me, because you normally write a paper and it's reviewed by other scientists. And so, you know, making agreement with policymakers is very difficult. So.
Absolutely. And I think it is definitely important that we do, like, our academic work does translate to them and they're in agreement, because in the end, they are the ones who have to drive the action. And so I think it might have been very difficult, but I hope that the results are more promising for the planet as well. But, you know, thank you for clarifying that. I actually initially was really skeptical of being the moderator of the talk, because I'm less qualified than Dr. Amna to moderate the talk. But then a lot of what you're talking about is really close to home, not only for me, but I'm sure everyone from Pakistan and elsewhere in the world who's sitting in the audience. My hometown, which is in the HKH region, the Hindu Kush Himalaya Karakoram region, you know, hosts more than 5,000 or around 5,000 glaciers. And in my lifetime, when I was young, I think there were 1 or 2 GLOF events. But in post-adulthood and in the most recent times, there have been so many GLOF events, and there's such a recurring phenomenon now, and the impact on the livelihood, you know, not just in terms of charging and recharging the Indus River, but also how it impacts those small valleys that live by it. You know, it's very evident, and I've seen that in my lifetime. But these regional small scale impacts are obvious to us, you know, people who are living close to them. But what do they mean? Like, what is this melting, and how do you think this melting would impact the changes on the global scale for high altitude and mid latitude glaciers in general?
Yeah. So so I'd say, just as an aside, I think, you know, because the regional information is so important, it's really important to have authors from all the different countries who can bring that local knowledge to it as well. So you know, I don't know, for example, just as an aside, if anybody did think they wanted to do it in the future, I'm very happy to talk to people about being involved in the process. But, you know, one thing we really tried to focus on in this report was to take it not just from the global message. You know, I think everybody's heard for many years global temperatures will warm and so on, but to try and kind of really understand the regional. And so if you look not just in chapter 9, but also in chapter 12, for example, of the report, and also the atlas, which has both a written part but also an interactive part where you can look at figures. You know, the regional information is really important there, you know, to try and give this bigger picture. And, you know, particularly in the glacier part, and this is what we looked at in chapter 9, was looking at this kind of both the global nature and also these individual regional changes. And it's quite, you know, glaciers can be much more sensitive, in particular to, you know, small scale weather changes, and as we've seen, as I talked about, you know, sometimes if the air temperature, for example, you know, changes because of the weather patterns, that can actually make glaciers start to grow rather than decline, you know. So there's a lot of subtleties at that sort of regional scale, but I still think in the assessment you do see this kind of overarching pattern emerging. Does that answer your question?
Yes, absolutely. And actually it also then connects
You're muted.
where to, can you hear me now?
Yes.
Okay, so I think it also connects very well to the next question that I have to ask, which is more to do with, yes, Amna?
We have an audience question if you would like to take that, and then we're also over time. Just pointing it out, sorry. No need to stop, just pointing it out.
Awesome, okay. Okay, so I think I'll continue with the question which has to do with the sea level rises, and you know, like you said, more local events were taken into account, and so if the local sea level rises, does that in any way reflect with the global? And I know you touched upon this in your presentation, but how do you think it would impact countries like Pakistan, Bangladesh, or other India and other countries in our region?
So you know, global mean sea level rise is a good indicator of coastal region, of sea level rise in coastal regions. I looked particularly, and you can look at how different components affect the pattern, because like gravitational effects can, for example, like if Antarctica melted, it would sea level would actually go down near Antarctica, whereas further north it would increase. So I've looked around the Pakistan, Bangladesh area on the figures, and I don't think I think all the contributions are pretty even there. So it would be much closer probably to the global mean sea level than perhaps some other regions might be. But there's a lot of different effects, and that's why I think that NASA sea level tool is really good for people. You know, people can look at details in that.
Okay, wonderful. Thank you. And I was hoping that I would not ask any question relating to climate denial, but the question that we have from a participant actually is relating to that, but more onto the quality of the work, and based on the quality of the IPCC report and the kind of facts and figures that have been reported. They think that because the interpretations lead to a more natural physics phenomena rather than human impact, although I did see some GHG related work that you shared as well. But as per the question, they think that most of the people criticize that the findings cannot be traced back to human action, but to physical phenomena. And they want to know to what extent this criticism is true. And this is from all the podcasts that they've listened to on that.
Yes, yeah. I think, as you see in that summary figure that I showed with the diamond, there's a lot of the changes you can see due to human influence. That's definitely the case in the ocean and cryosphere changes. In fact, in the review comments, I was actually surprised I expected to have a lot of review comments on the report where people claimed that this wasn't human influence and so on, but actually there were very few in our chapter. So I thought, and they will be on the public record, the review questions, so people can look at them. There were a very small handful of those, and we actually probably had more comments from people who said we didn't kind of show enough of the low likelihood, high impact. So I kind of thought that the argument had gone the other way a little bit, but I would say, our evidence would suggest that it is human influence, and so I'd refer people back to that figure.
Absolutely. And Dr. Helene, this
You're muted again.
I hope you can hear me now. Okay, so this has been an absolute honor listening to the work, but seeing the work of all the other scientists and academics, and also you've made it easy and accessible for people like us who understand but would need to read otherwise a lot of stuff to get through it. And I'm sure that Amna and I are in the waiting list of wanting to be IPCC chapter authors. And we look at your journey and we find it incredibly inspiring, because you do look very, very young. And so I think, and this relates to the other question that's put in the inbox chat box in a way, that could you tell us about your journey of becoming such a young lead IPCC author, and your journey of leadership in general, as well as the future you see for yourself, as well as for young academics across the world?
Yeah, well, I just started my career. I did maths at university. I did a PhD in physical oceanography, and then I went to work at the Hadley Centre, which is part of the Met Office. So I was, the Hadley Centre has got a long association with IPCC. One of the first co-chairs, John Horton, was at the Met Office. So it was kind of things, I was more familiar with it. So I probably was lucky that I had a lot of role models. But I think, I'd got involved through in previous reports from reviewing chapters, which anybody can sign up to do. So that's a really good thing to get involved with to start with, by being a contributing author. Sometimes that sort of involves like trying to talk to the authors. So getting to know people in the community. And I'd be really happy to talk to you all some more in an informal way. So, please do email me, anybody who wants to. And I think people are really looking to, in the community, people are definitely looking to engage with people from a wider span of countries. I think, probably back when in the first IPCC report, it was probably very much kind of Western Europe, America, I would say. I haven't looked at the authors, so I don't know that for sure. That might be my sense. I think that's definitely not the intention moving forward. So I think there's lots of opportunities. So read the IPCC reports, get involved in things like look what WCRP are doing. There's lots of committees you can get involved with, and conferences, and a lot more virtual conferences. So I'd really recommend kind of those sort of approaches. And what am I going to do in the future? I'm not going to be a coordinating lead author again. I lost a lot of sleep over 4 years. But I am definitely going to stay involved, and I'm really looking forward to kind of doing more kind of leadership things, both nationally and internationally, in what I do.
Well,
and hopefully maybe I'll be a review editor for IPCC.
Thank you so much. And I think with that, I can pass on the floor to Dr. Amna. And thank you once again, Dr. Helene. It was a pleasure.
Yes, I think I will wrap it up now because we have taken more time that we asked Dr. Hewitt to give to us. So if there are no more audience questions, I think we'll wrap it up. And oh, we do have a question. Oh, I will let you know, Nimra. We will put it up on our webpage. So thank you, Dr. Hewitt. Do you have any questions at all for us?
No, I'm just putting my email address in the chat. So if anybody wants to contact me, then I'm very happy to talk to people. I'll try and respond as fast as I can. But and really keen to support anybody who wants to kind of be involved moving forward. So
thank you so much.
Thank you.
Thank you. Bye.
Thank you.
Bye.
I end it, right?
I think you should end it.
Yeah, I have like my finger on it. So, okay, I'm going to end it.